Thank you for joining this lesson. We're going to discuss gas laws. Before we begin the lesson, remember you can consult us through our line here, 0704 153 366. You can also contact for online classes. We are told in part A, number 16, to state the pressure law of an ideal gas. And the pressure law of an ideal gas states that for a fixed mass of a gas, the pressure is directly proportional to its absolute temperature, provided the volume is kept constant. Therefore, mathematically, we can say that pressure is directly proportional to T. And remember, when you are stating the law, you should stick to the meaning. So you're not supposed to paraphrase the statement of a law or any principle. Its absolute temperature. When we talk of absolute temperature, we mean temperature in the Kelvin scale. Therefore, you are not supposed to interfere with such a term. In part B now, we've been told that the pressure P of a fixed mass of a gas at a constant temperature of T equals to 200 Kelvin is varied continuously and values of corresponding volume recorded. Then a graph P against 1 out of V, so the reciprocal of volume now, is shown on the grid below. So on the grid below, we have a graph of pressure times 10 power 5 in pascals. Then this is against 1 out of V, which is in per cubic meter. Determine the volume of the gas when the pressure reads 2.8. This is 2.8 times 10 to the power of 5 pascals. Therefore, we go to the axis of pressure and we read the mark that will show us 2.8. Remember, the scale here means if this is 0 to 1, then 1 to 2, 2 to 3, it means for every small division, there is 0.1 units of pressure. Therefore, our 2.8 is going to be two small squares just below 3. So this is 2.8 times 10 power 5 pascals. Now we're going to move along this line until we cut the graph. Then below the graph now we can read the value of 1 out of V. That is what we're going to do. So when you move along, now we are supposed to read after the graph has intersected with the line showing us 2.8. Now we get down to read the other quantity here, which corresponds with 2.8. And remember, the other quantity is not volume, but 1 out of V. Therefore, the value of 1 out of V becomes, this is 50. These are 10 divisions until we get to 60. Therefore, it means for the 10 small squares, we have 10 units. So for every 1 unit, there is 1 small square. Therefore, this is going to be 56. This is going to be 56. So it means at that point, the value of 1 out of V equals to 56. And the units are per cubic meter, not even centimeter, per cubic meter. That means for us to get volume, now we need the reciprocal of this value so that we get volume in cubic meters. That is what I'm going to obtain right away. So I'm going to say 56, then I get reciprocal, and this gives me 0.01786. Now meters cubed. This value can be written better as 1.786 times 10 to the power of negative 2 cubic meters times 10 power negative 2 cubic meters. We can continue doing questions from the same graph. Now we are told in the next page that find the value of R, given that find the value of R given that the pressure P and the volume V of the gas are related by T equals to PV out of 2R. This is the equation relating where r is a constant. Where r is a constant, we are finding the value of such a constant. Now, for us to get the value of such a constant, we are supposed to know that from the graph, we have plotted P against 1 out of V. And if we can rearrange this equation and we have V and P rearranged so that we have P taking or being the subject, in other words, so that we may arrange the equation now in this format, then that will be better and that will help us to find the value we want. Therefore, in this case, I can multiply by 2r out of V to remain with P alone. I can multiply with 2r out of V. Therefore, I'll find T here. Then I've multiplied it with 2r out of V. Yeah, so times 2 times 2r over V, also times 2r over V. So this is now will be now the expression. So a change of this expression to P equals to 2t r out of V now makes it better for interpretation. Now for us to interpret, we should know that P has been plotted in the y-axis and 1 out of V in the x-axis. So that means the coefficient of whatever is in x-axis, according to the general equation of a straight line, we should be able to interpret every plotted equation. Therefore, on this side, because 1 out of V is on the x-axis, we can actually say this. We have 2t r, then 1 out of V, which is on the x-axis. So the coefficient of x-axis quantity now becomes our slope. Therefore, the slope of this graph will be given by the value of m, which is the coefficient of 1 out of V, and that is 2tr. 2tr. 2 is a constant and T is the constant temperature, which has been already provided. We are told the temperature T is 2000. If temperature T is 2000, now it means after getting the slope, now we will get to 2 times T, so that the unknown remains R. Let's get the slope first. We need change in Y out of change in X. So change in the pressure out of change in the 1 out of V. This is going to give us the slope. Let me get any two coordinates which are lying on the line so that we may get the slope. Any two coordinates. So any two coordinates, we can even pick as early as from here. This is going to be 20 and 1.0. A coordinate like this, which is 40 and 2.0. So we can use those coordinates for us to find the slope. So for us to find slope of this line, now we need the two coordinates 20 and 1, then 40 and 2. So we can take change, a change in y, which means 2 minus 1. So we can take 2 minus 1. So 2 minus 1, but we should remember for this one, times 10 power 5. Then we divide by 40 minus 20. Yeah, 40 minus 20. This is going to be, this is 1. So it will just be 1 times 10 power 5 divided by 20. So when we get this value, let me compute it. Times 10 power 5 Then we divide this by 20. This is going to be 5,000. Strictly 5,000. So the value there is 5,000. When the value is 5,000, I think it's also good we work with the SI units. Remember, I'm dividing pascals. This is pascals divided by, it was already 1 over V divided by 1 over V, 1 over meter, 1 over meter cubed. So we can multiply this with meter cubed. So this is pascals times meter cubed. Pascals times meter cubed, or rather newtons per meter squared multiplied by meter cubed. And this will make it, this is going to make it Newton meter. So the value of the slope, I'm trying to derive the units. I've said these are pascals, which are equal to Newton per meter squared. So this value of 5,000 is equivalent to, it's already Newton per meter squared. That is the units of pressure, the equivalence of 1 Pascal. Then dividing by 1 out of meter cubed means times meters cubed. So meters cubed cancel, and this will be 5,000 Newton meter. So that will be the value of our slope. And remember, our slope is equivalent to all this. So for us to get R now, as required from us, we should say that 5,000 Newton meter is equivalent to 2 multiplied by T equals to 200 Kelvin multiplied by the unknown R. Therefore, for me to remain with R, now I'm supposed to divide 5,000 by 400 Kelvin. So out of 400, this becomes 12.5. These are now Newton meter per Kelvin. We should again work on this unit. Newton meter, according to work, is equal to joule. So the value of R is going to be 12.5 joules per Kelvin. Joule per Kelvin. Now you see, this is a heat capacity. Joules per Kelvin. It's not even when we talk of per Kelvin, we mean heat capacity. So these are the units of heat capacity. Joules per Kelvin. So that is the value of R and the respective units. We can now finish up by finding, because we are told the pressure of the air in the car tire increases if the car stands out in the sun for some time on a hot day. Explain the pressure increase in terms of kinetic energy. So we are explaining increase in pressure following kinetic energy or kinetic theory of gases. We are told that when a car is outside on a hot day, the pressure increases. We explain this. Now, we are supposed to write this, that increase in temperature, because it is a hot day, in temperature of course of the air increases the kinetic energy of the gas or of the air, making its particles to vibrate faster or more vigorously, making the particles of air to vibrate faster. Then we can say, now that the volume is fixed for this tire, then these collisions now, this increases the number of collisions. The number of collisions between the air particles and the walls of the tire. The walls of the tire per unit time. Per unit time, hence increase in pressure. So that is what constitutes to the increase in pressure. Increasing temperature increases the kinetic energy of the air particles, making the particles now to vibrate faster. This increases the number of collisions between the air particles and the walls of the tire per unit time. Therefore, how the particles of air could collide with the walls of the tire is now increased. The rates are increased, and hence the pressure will increase. Remember, pressure is due to collisions. Therefore, the collisions per unit time increase, and hence increase in pressure. Finally, we are told in part D, a gas is put into a container of fixed volume at a pressure of 3.0 times 10 power 5 newtons per meter squared and temperature 27 degrees Celsius. The gas is then heated to a temperature of 177 degrees Celsius. Determine the new pressure. If the pressure is changing due to change in temperature, we are supposed to know that this is a pressure law, and we say that the pressure is directly proportional to temperature. So that means pressure equals to a constant times temperature. So a constant is given by pressure out of temperature. And if the pressure is taken to a new temperature, we will also have a new pressure. And if another variation is done, we will still have a new pressure and a corresponding new temperature. But we should know that for such a case, the constant remains the same. And that's why we resolve that. When we take now P out of T1, this should be the same as P2 out of T2. Because when you change temperature, the pressure changes correspondingly or proportionally, such that they will give us the same constant. So these two are equal. And that is why when we take the first pressure of 3.0 times 10 to the power of 5 and we divide it with the initial temperature, which is 27 degrees Celsius. Now we have to make it absolute temperature. So 27 plus 273, this becomes exactly 300 Kelvin. This is equal to the new pressure, which is unknown, out of the new temperature, 177 plus 273. This becomes 450. 450. So we can get now our new pressure, P2, which is going to be 450 by 3.6 times 10 power 5. Then we divide by 300. This becomes 5.4 times 10 to the power of 5 pascals. So that is how we get the new pressure. Thank you for following.